fast. As always, whether you're a student or not, or you're not one of my students, if I've glossed over some material and you don't understand, please ask questions. If you're confused, you just don't get it, please ask questions. All right, guys, so today we're going to talk about Chapter 18 and welding variables and parameters of different types of materials and kind of what we should do. So let's get the show on the road. All right, so the first thing we're going to talk about is carbon steel. So there are different types of carbon steel. First, there is mild or low carbon steel, otherwise named as ASTM A36. Okay, this is the most common steel you're going to see, and it's really easy to weld. Okay, then there are medium and high carbon steel. So what makes the medium and high carbon steel so special? Well, when we talk about them, we're actually stating how much carbon they have in them. Okay, the more carbon, the harder and stronger they become. But this also makes it more difficult to weld. More carbon, harder to weld. Okay, so there's that toss-up. So when carbon is over around 0.03% or more, it's considered medium or high carbon steel, and we need to preheat it and post-heat it. Okay, if you don't preheat and post-heat, you're going to lose that toughness and ductility, and in the end, you're going to have a crack. Okay, so let's look at the chart. So we need to remember rule number 3. Rule number 3 says what? It says 90% of what we do is dictated by thickness of material. So let's look. So if I have a 16th material thickness, I'm going to use a 16th diameter rod, and I'm going to use between 100 and 140 amps with 20 CFH thereabouts. Okay, so this chart shows us approximately amperages for thickness of material and filler metals. So how do we really determine the correct filler metal size? Okay, so this chart, it kind of gives you a good jumping off point. Personally, I try to make sure that the filler metal is not any bigger than the thickness of my metal. If we really think about it, let's think about it. Let's go there. So if my material is really thin and I'm using a thicker filler metal than my material, what's going to happen? Well, in order for my filler metal to melt, I'm probably burning the base metal to a crisp. Or if I get my base metal to puddle and I stick that rod in there, what's going to happen? Stick city, right? Okay, so we need to think about that, okay? But what this chart doesn't show is the size tungsten that should be used. So remember, the smaller the tungsten, the less current is required to start it. And it will have a smaller or lower maximum amperage. So say we're using 1/16 inch tungsten. Okay, the starting amps around there are about 5, and it goes to about 90 amps without melting it down. Okay, so if I start to go over those amperages, I risk melting down the tungsten and have bad things happen. We don't want to do that. Okay, you can have your torch, pretty much melt in your hand. It's all bad. Okay, so if I have a larger tungsten and thinner metal, what's going to happen? Just starting the arc to have enough current to go through that tungsten, I'm going to blow right through that material. Okay, so we need to also keep that in mind. So like I said, 90% of what I do, or what we should do in welding, is dictated by thickness of material. Okay, so larger tungstens also allow you to put more current through it, so it's more able to work with thicker materials. We can use higher amperages. All right, so the next up is stainless steel. All right, come here, stainless steel. All right, so here it is. So remember, stainless steel has chromium and nickel coating that gives it that corrosion resistance and heat resistance. So if we put too much heat into it, we're going to burn off the important stuff to make it stainless steel. Okay, so this means that you need to really pay attention to your heat input. So again, rule number 3 is in play here. It dictates everything you do, and in this chart it also shows us what? Electrode diameter, aka your tungsten. So when we weld stainless steel, we want to also over alloy to avoid cracking. What does that mean? It means we want to put extra alloy to help it not crack if the base metal becomes too hot or we lose some of those alloying properties of the base metal. So for example, when we use a 316 stainless steel, we have a lot of choice of filler metals, but we can go with a 316 or a 316L. The 316L tells us that it has more alloying material and we want to use it. I'm going to attach a specification sheet, but pretty much what it says is the difference between 316 and 316L is that the 316 has more carbon than the 316L. The L is for low carbon. 316L also has more alloying materials like molybdenum. Okay, so it's really cool. I'm also going to give you a link for Lincoln Electric. It actually talks about when to use particular stainless steel rods. I thought it was really helpful. Okay. All right, so we kind of see that jumping off point, and I think this is kind of important for you guys to look. It's in your book, and I think it's kind of helpful. It gives me some jumping off points of what I might want to run at, okay? All right, here we go. Aluminium. All right, so there are so many considerations we need to think about when we think about aluminum, but I'm going to preface this. When we TIG weld, we need to make sure that we have good joint cleanliness, good material cleanliness, good filler rod cleanliness. This will help avoid 90% of the problems that you're going to have with any type of alloyed material, non-ferrous materials, or anything like that, because we're just going to avoid it. Okay, so first, when we talk about aluminum, aluminum's properties actually depend on the oxide coating. That oxide coating helps it not to rust. Okay, so, but this oxide coating melts 3 times hotter than the aluminum itself. So, if you don't remove it, you can end up with issues. So, how would I remove it? Well, I either grind it, I can sand it, I can wire brush it, and then I can also use acetone. Okay, so what happens when we don't clean it right? Well, the weld just doesn't come out when you weld it. It almost seems like it's gummy or the bubble is just stuck under there and it doesn't break through. It has some sort of covering. Well, that covering, that's oxide. Okay, so another issue that if you don't take that oxide out is oxide inclusions. Since those oxides are also heavier than the aluminum, it can sink to the bottom of your weld and create oxide inclusion. So pretty important, right? Cleanliness is important regardless of the material you're using, okay? They say nickel alloys require what? Joint cleanliness. Magnesium requires joint cleanliness. Okay, guys, get the picture. TIG needs joint cleanliness. Okay, so when we also do aluminum, we're also going to use the AC. That cathodic bombardment, bing, 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 it also blows off some of the oxides in the material. So we're kind of hedging our bets. If we clean it well, we use the acetone, and then we're using AC. But what happens when we use DC electronegative? Because it can be used with aluminum. Well, you don't get that cleaning action like you would with AC. So you need to make sure things are extremely clean. All right, so when you're welding thin aluminum, anything less than 1/8 of an inch, it's also a good idea to use a copper backing bar. What does that do? Well, it acts as a heat sink. It helps keep the heat in there so that you can actually weld it well. I'm going to use them on thinner gauge materials, okay? So remember, aluminum has a high thermal coefficient. This means it takes a lot of heat and dissipates it fast. Also, aluminum has a high thermal expansion. What does it mean? It means when it gets hot, it gets bigger, and cooler, it gets smaller. So this can lead to issues with cracking if we don't have enough filler metal, and that it doesn't counteract that expansion and contraction. This is why when we do aluminum, they tend not to use a filler metal and not use a autogenous weld or a fusion weld, because when it contracts and expands, it's going to crack down your weld. Okay. So this can also cause a problem when we have dissimilar metals. If I have a metal that has a different thermal expansion rate, we can have an issue. Okay. All right, next up, magnesium. All right, we're going to think about mag rims, okay? Magnesium is used for what? Well, we're going to use it for a high strength to weight ratio, which means it can be extremely thin, if you see here, but extremely strong, okay? But we're also going to use a lot smaller electrodes. We're going to use a lot less current, and we're not going to do any out of position welding, meaning flat or flat, okay? So magnesium is also said to weld kind of like aluminum. Okay, so AC can be used with helium, argon, or an argon-helium mixture when we weld metals 0.20 to about ½ inch thick. Okay, you can also use DC electronegative, but there's no cleaning action, but there's better penetration. With helium, especially when welding thicker stuff, it's a lot better. Okay, so I've seen and used helium and DC electronegative, and it's kind of cool. Okay, so magnesium also requires a preheat and a slow post heat to avoid cracking. Okay. Other than that, we're really going to use pretty much the same variables based on thickness of material. And if we really look, these are pretty comparable to what we might see with aluminum, but this isn't really going to be so thick. We remember anything, greater than 1/4 inch, we're actually going to have to put some sort of edge preparation on this. So, we're topping out at 130 amps. Okay, we're not having to put a whole lot of heat into these. All right, next up. This is almost laughable, guys, but I love it. Oh, come on. Next up is deoxidized copper. Okay, so deoxidized copper, they say, is most commonly welded copper, and they say it closely welds like mild steel. Personally, never welded copper. I really haven't found the need, but it can be done. The other thing is, if you're going to weld on copper, copper gives off extremely toxic fumes when it's welded. So you should have an extremely good ventilation. This just doesn't mean you're not welding in an open room, okay? So we're going to base everything on thickness of material, okay? So if you're welding copper that's over 1/4 inch, it needs to be preheated between 300 and 500 Fahrenheit. And they say that when we weld copper alloys, we want to use a forehand technique. So of course, good ventilation is important with copper and copper alloys. Now, what would be a copper alloy? Here it is. Here's our copper alloys. This might actually be more towards like brass or something like that, or silicone bronze, or some sort of mixture like that, okay? And we're going to use the same thing. We're going to base this on thickness of material, okay? And we're really having to pump up. Really think about it. This is 1/16 of an inch, and we're topping out at 130 amps in flat position for 1/16. Okay, guys, so think about this. We're really having to put a lot more heat into this material. Okay? All right, onwards. All right, guys, so points to remember. Filler metal containing the oxidizers should be used to prevent porosity, okay, because the oxidizers help take out all the, well, let's talk about the word. DE is of or not, oxidizer, oxygen. So it's taking out the oxygen. Medium and high carbon steels require preheat and post-heat to avoid loss of toughness and ductility because of carbon. We want to make sure there's good ventilation. A lot of these alloyed materials are really toxic, not good for you. Okay, when we weld light gauge metals, meaning thin, a copper backing bar is used. And if we're going to weld thin copper, we're going to use a steel. Okay, all right, next up, questions for study and discussion. As always, take care.